do to get some points back. And then our final exam is scheduled for Friday, the 20th at 3. I'm going to hand out this practice final exam. Please read the top page like carefully. It should answer pretty much all the questions that you might have about what to expect. If there are questions that are not answered on it, please let me know. Same note card rules. So like the one thing it doesn't mention on there that still holds here is that if you don't use a note card, you'll get 5 bonus points. Okay. Should we start? Maybe. Are you guys okay?
Oh, sorry.
Okay. Okay. Good. Okay. So we're going to do the first section here today. Looking at parametric equations. And we have seen, if you took calculus at Vermont Tech, when we got to the applications of the derivative part, we actually saw parametric equations a little bit when we were doing curvilinear motion. We said, oh, instead of just thinking about a curve in rectangular coordinates like y is a function of x, which could certainly describe the path something follows. It could tell you where it goes, but it doesn't tell you when it gets there, like maybe what direction it's going in. What we would do sometimes is parametrize that equation. So instead of having just y as a function of x, we could turn it into two equations, x as a function of t and y as a function of t. So you would just sort of let t go through all these values. For each value of t, you can get an x coordinate and a y coordinate, right? Kind of plot that way. Those are parametric equations. So we call that extra variable t, we call that the parameter. And then the set of points that you get as t varies over some interval can give you a graph of the parametric equation. We call it a plane curve or a parametric curve. And when you have a parametric curve, a natural thing that we might think about in calculus is how do we get the slope of a line tangent to the curve? Which is to say, how do we get dy dx? When you have y as a function of t and x as a function of t, how do you get dy dx from those other derivatives? And basically, I think this sort of makes sense. Dy dx is equal to dy dt over dx dt, in that you kind of treat these dx dt and dy dt as though they're fractions, like dy dt divided by dx dt is dy dt times dt dx, right? Like kind of multiplying by the reciprocal, and dt dx, and then you get dy dx. So that's sort of the idea behind that. And of course, this last piece is important, granted that dx dt is not 0 because we can't divide by 0. So if I want dy dx for this curve, x is equal to sine t and y is equal to cosine t, then we just find dx dt and dy dt first. So if x is sine t, dx dt is cosine t. And if y is cosine t, dy dt is minus sine t. And so that means that dy dx is dy dt divided by dx dt. That gives us minus sine t over cosine t, or minus tangent of t. Note that when we find, we're starting with parametric equations like we had, x is sine of t, y is sine of cosine of t. When we start with those parametric equations that are expressed in this case as functions of t, when we find dy dx, we still get a function of t. Right? It doesn't change it into a function of x. We can use the same definition up here, or in Theorem 33, I guess, to find higher derivatives. So if we move down here into Theorem 34, I'll kind of talk about it in a little bit of detail in the second derivative, but then that sort of leads naturally. Just so when we find the second derivative, d squared y over dx squared, second derivative of y with respect to x. That is the derivative with respect to x of dy dx. That's what it means to take a second derivative. Just differentiate that derivative with respect to x. So using Theorem 33, I'm going to take the derivative with respect to t of dy dx and divide that by dx dt. Just like when my function was instead, when I was looking for dy, the first derivative, dy dx, I just took the derivative of y with respect to t and divide by dx dt. In this case, my function is dy dx, so I'm going to take the derivative with respect to t of dy dx and divide that by dx dt. We get the same thing if we're finding the third derivative. So this time, my function that I'm differentiating is a second derivative, so I'm differentiating that with respect to t on top, and then still dividing by just dx dt in the bottom. So here they've given us a curve defined by these two parametric equations where t is greater than 0. We want to find the slope and the concavity at the point 2, 3. So we know that if we want the slope, we're going to find dy dx. And to find concavity, it's been maybe a little while since we've done this because this was a Calc 1 thing that we did when we were doing curve sketching, but concavity we get by finding the second derivative of y with respect to x. So we're going to find these and then evaluate them at that point, 2, 3. So x is the square root of t, or t to the 1/2. dx dt is 1/2 t to the negative 1/2. Our y function is 1/4 t squared minus 4. So dy dt is 1/4 times, and then the derivative there is just 2t minus 0, so 2t, and then we get 1/2 t. So we have the pieces we need to get dy dx. Right, dy dx is dy dt divided by dx dt. So that's 1/2 t on top over 1/2 t to the minus 1/2 on the bottom. The 1/2s cancel, and t over t to the negative 1/2 is t to the positive 3/2. So there's the derivative of y with respect to x. We haven't actually found the slope yet, and we will in a bit. But first, I just want to see if there's questions on how we got this far. Okay. Okay. So before we evaluate and find the slope, let's go ahead and find the second derivative of y with respect to x. So we're going to take the derivative with respect to t of dy dx, and then divide that by dx dt. So dy dx is what we just found. We're going to differentiate that with respect to t and put that up top. So it's a power rule. We get 3/2 t to the 1/2, and then we're dividing that by 1/2 t to the negative 1/2. There's our dx dt. And then we simplify. So 3/2 divided by 1/2 is 3. T to the 1/2 over t to the negative 1/2 is just t. So we get 3t. So those are both the function. There's a first and second derivative of y with respect to x. Questions on how we got either of those? So now that we have those, we can see what's going on at the point 2, 3. So those are rectangular coordinates, right? That's a coordinates of a point where x is 2 and y is 3. We'll note that we have these derivatives as functions of t. So one of the first things, or the first thing we got to do before we can get those values, is figure out what t is. What value of t gives us that point. So when x, y is the point 2, 3. Really, they could have just given us one of those points, but one of those coordinates. Both of these coordinates are met at the same value of t. So let's say if we pick x equals 2, that means that, let's see, the function for x was x equals t to the 1/2. So that's the square root of t equals 2, and we get t equals 4. Note that they told us that t starts at 0. And so now we can find the slope. So we're going to find dy dx at t equals 4. And our dy dx was t to the 3/2, so that's 4 to the 3/2, so square root of 4 cubed, 2 cubed is 8. So certainly it's increasing. So for concavity, we'll do the same thing, but with the second derivative. So we're going to find d squared y dx squared at t equals 4. And that is, let's see, that was 3t, so 3 times 4, or 12. What can we say about the concavity? Does anybody remember how this works? Concave up, yeah. Your calculator, the TI-84, TI-83, they can graph parametric equations. They can show you what the curve looks like when you give it a pair of parametric equations. So I just want to show you how that works. So normally our calculators are in function mode. And when you're in function mode, then when you hit the y equals button, it's just ready to give us, like, to take y as a function of x, what we call the rectangular equation. Instead of being in function mode, we want to switch to parametric mode. So I go down to this line, and mine, depending on what version you have, it either just says PAR or it will spell out the word parametric. So just select that. And when it's on parametric mode, now when you hit y equals, it gives you a pair, like x1t at y1t. That's a pair of equations. And, you know, x2t, y2t. So it knows to expect two equations. Also, you know how next to the alpha key is the variable key, like it says x, t, theta, n. Depending on what mode you're in, when you hit that key, it'll either give you an x or a t or a theta. When you're in function mode, it's always x. Now that we're in parametric mode, it'll switch to a t. So I could put, ours was t to the 1/2, or square root of t, and then 1/4 parentheses t squared minus 4. So we've entered our equations. Now hit window. This is usually where we just set the x and y ranges on the coordinate axes. Now it's going to want more. So it still has the x min, x max, and y min, y max. Now it also wants a t min, a t max, and a t step. So it wants to know, where does t begin, and they told us that it starts at 0. A t max, let's see, the point we're interested in we found is when t equals 4, so maybe I'll go t equals 5. And then a t step. Basically it's asking, how often do you want me to stop and calculate coordinates of a point? The smaller your t step is, the longer it will take to graph, but also like maybe the smoother the curve will appear. So maybe I'll put it at like, I don't know, 0.01. And I'm not sure exactly, I'll go from -10 to 10 on the x and y axes. And now I'll hit graph. So there it is. That's only going from t from 0 to 5. I could make it go further, you know, t max up to 10 or something. So the 0.23, and I'm going to adjust the window a little bit. I'm going to make my x's start at 0 and my y's start at maybe -2, just to have a... Okay, so this was the 0.23, guess that's right around there that we were looking at. Certainly is concave up, and it is increasing. How we doing? Okay. Should we do some more? Maybe? The cool thing about parametric equations, and this will also be true for the polar curves when we look at those, is that you really get kind of cool looking curves when you allow yourself to use parametric equations. Like in regular function mode, or writing y as a function of x, you probably would never end up with a curve that looks like this, because y is not a function of x, right? Like it fails the vertical line test. But you can get kind of interesting curves by using parametric equations. So in this problem, we have x is 2t minus pi times sine t, and y is 2 minus pi cosine t. It crosses itself at the point 0,2. Okay. Find the equations of both tangent lines at this point. So they kind of sketch those blue lines there in the figure. And they even told us what values of t. So the one with the negative slope, that's t equals negative pi over 2, and the one with positive slope, that's t equals pi over 2. The way that we would get that normally, I mean, they gave that to us here, but the way we could always find that, just like we did in the last one, is we say, okay, x is 0 and y is 2. Pick one of those values to use and give yourself an equation. So when I look at these two equations that they gave us, the one that seems like the easiest to use is the y equation, because it's just a constant minus pi cosine instead of this linear term minus pi sine. So I'm going to use that one. So 2 minus pi cosine of t is equal to 2. and we can subtract 2 from both sides. We end up getting minus pi cosine t is equal to 0, and that means that cosine of t has to be 0. And cosine of t is 0 at the top and the bottom of the circle. So this is where t is pi over 2 and negative pi over 2. You could argue, well, that also happens at 3 pi over 2 and 5 pi over 2, all odd multiples of pi over 2, right? Because cosine just keeps going around and around the circle. But these are the only ones for which x would also be equal to 0, because I think if you tried the other ones, you would find that the x coordinate didn't line up. Okay. Why not? When you plug it into the x? So sine of negative pi over 2 is negative 1.
But that makes the first part negative.
Yeah, I think that works. Yeah, because then that's pi. Yeah, because then that's negative pi plus pi. Yeah, okay. Good to check. Yep. So we've got our value of t. What did we want to do? We wanted to find the equations of both tangent lines. So we have the point. The point is 0, 2, right? So we just need to find each of these slopes. So we're going to find dx dt and dy dt, right? And then use theorem 33 to get dy dx. So if x is 2t minus pi sine t, then dx, what do we get for dx dt?
2 minus pi cosine t.
2 minus pi cosine t, and then if y is 2 minus pi cosine t, what is dy dt? Pi sine t. Yep. So we put this together. Dy dx. Okay, so dy dt goes on top, so that's pi sine of t over dx dt. 2 minus pi cosine t. And then we get our slopes just by evaluating these at the two values of t that we found. So when t is negative pi over 2, dy dx is pi sine negative pi over 2 over 2 minus pi cosine negative pi over 2. Sine negative pi over 2 is negative 1, so that's negative pi over cosine of negative pi over 2. Yeah, so then we get 2 on the bottom. Oh, so negative pi over 2. Okay. And then when t is pi over 2, cosine pi over 2 is still 0. Sine of positive pi over 2 is 1. So we get positive pi over 2. And now it's all over but the shading. We're just going to get the tangent lines. So when t is negative pi over 2, we have y minus 2 equals, let's see, y minus 1 m, so it's negative pi over 2. X minus x2, x was 0, so it's just negative pi over 2x. And at t equals, oops, that's negative pi over 2. When t is positive pi over 2, it's y minus 2 equals positive pi over 2 times x. These are just point slope form.
Do you have another packet by chance?
Yeah.
Got it out of my physics lab earlier. If done, I can just watch.
No, I think I got it.
Okay, thank you.
Okay. So this was all they asked for. Are we having fun? Mostly? I will answer the questions I pose to the class, I guess. Yes, for mostly. What's that?
Can we put it in slope and stuff?
Sure. Other questions? Okay. All right, we're gonna finish up this section. We've got a couple of examples. One for finding arc length, and then one for finding surface area. We've seen these applications before, like it was closer to the beginning of the semester, I guess. We had these integral formulas that would give us the length of an arc, and this is just if you compare this to what we did before, it looks very similar. It was 1 plus the square of dy dx inside the radical, and so this time it's just the sum of the squares of dx dt and dy dt. So you don't have to memorize these. These will be, in fact, if you look at that practice exam that I handed out, you'll see this formula is on there. This is just the version that you use if you have parametric equations. We have to be careful a little bit. So let's see. This says if a smooth curve is given by this pair of equations, such that C does not intersect itself over the interval, except possibly at the endpoints, the arc length is given by this. So a smooth curve, usually a smooth curve is one that is like differentiable, not just continuous, but differentiable, meaning its tangent slope is well defined at every point over the interval. And I'm pointing that out because on this one, that is a continuous curve, right? I mean, there's no breaks in it. But there's definitely something funny happening here, and here, and here, and here. Like those, the curve is not smooth at these points. Like the derivative dy dx is not really well defined because like there's infinitely many lines I could draw that are tangent at that point because it comes to like a sharp point. So if we want the arc length that's traced over the whole circle, what we're going to do is take advantage of the symmetry that exists here and find the arc length for one of these guys, and then just multiply it by 4 because it's smooth on that single interval. Now this takes a little bit of doing, which I know we're all really pleased to hear, but it'll be pretty fun. And it takes a little bit of space. So like I'm actually going to start, because the y and x functions there are not super involved, at least they're not hard to take the derivative of. I'm going to find dxdt and dydt up here so I don't have to use up more of this space. So what do we get for dx dt?
Negative 5 sine t plus 5 sine 5t.
Mm-hmm. And how about dy dt?
Cosine t minus 5 cosine
5 cosine t minus 5 cosine 5t. Yeah. Okay, great. So let's see. I think next I'm going to do a little algebra. I'm going to take that dx dt and I'm going to factor out a 5, and then I like starting with positive terms, so I'm going to reverse the order of the terms. So I'm 5, and inside I'm going to have sine 5t minus sine t. And then I'll do the same thing with dy dt. I'll factor out the 5. I'm not going to switch around the terms because I'm already starting with a positive term. So cosine t minus cosine 5t. So I found dx dt and dy dt because that's what's in the integral formula above in theorem, whatever it is, theorem 35. So what I need to do now is square both of these derivatives, add them together, throw them inside a radical. So dx dt squared. If I'm squaring that product, I'm going to square both factors. So I'm going to have 25 times, and then I want to square, I want to FOIL that out, right? So when I square, I'm just going to FOIL it out. What do we get? Sine squared 5t minus 2 sine 5t times sine t, and then plus sine squared t. Going to do the same thing with dy dt. 25, and then foiling that out, cosine squared t minus 2 cosine t cosine 5t plus cosine squared 5t. Are we excited to add these up and throw them inside a radical? Because that sounds like a really easy integral to do. It's going to simplify kind of nicely. So don't worry, it'll all end up okay. So, all right, so our arc length is going to be 4 times the integral. Because we're only doing one of those, right? A quarter of those. And it can actually make that trip. This point here is when t equals 0, and this point up here is when t equals pi over 2. So we're going to just integrate from 0 to pi over 2 and then multiply that by 4. Okay. So in this, I mean, there's a lot going on in this radical, but first I just want us to see it as we're adding two things together, right? We're adding these two products. Like, I'm going to just sort of emphasize here that we have 25 times this plus 25 times that. All right, like forget about what's in the parentheses for a second, but we're adding those two things together, and those both have a factor of 25, which means there's a factor of 25 in the whole thing, inside the radical. So we can yank that outside the radical, it becomes a factor of 5. I want to do that first. And now now I don't need those big parentheses anymore. So sine squared 5t minus 2 sine t sine 5t plus sine squared t plus cosine squared t minus 2 cosine t cosine 5t plus cosine squared 5t. It doesn't feel like it made it that much better, but there's a couple things we can do to help simplify right now. So specifically, what happens if we look at these guys? That's 1, yep. And what about if we look at these guys? That's 1, yep. So I'm going to yank that 5 outside, so I'll have a factor of 20 times the integral 0 to pi over 2. Now I have, of course, 1 and 1 is 2, so we have 2 minus 2 sine t, sine 5t, minus 2 cosine t, cosine 5t. Now I'm going to make one thing that looks like a leap. I'm going to tell you how it's done, and I'll share some more detailed work, but it takes a few minutes to work out. It's a trig identity. It's one that we don't employ very often, but if you use one of the sum to product formulas, you can show that this part here you could show that that is equal to negative 2 cosine 4t. So in the radical we have 2 minus 2 cosine 4t. And I'm going to add a page here. I know I have magic paper, so. So then the other thing we'll do is this piece here. Whoops. We're going to use the double angle formula for cosine. There's actually 3 versions of that, but the double angle formula for cosine, the version that we'll find most helpful, is that cosine 2 theta is 1 minus 2 sine squared theta. And so that means that we can replace cosine 4t with 1 minus 2 sine squared 2t. And I promise that this would simplify nicely, and it will. I'm going to distribute that 2. So we have 2 minus 2 plus 4 sine squared 2t. And already right now is when you're starting to get that feeling like, oh, this is feeling so good because I can see how nice it's going to simplify. Or you're feeling, oh my God, can this just be over soon? Either way, yeah, it's going to be over soon. So the 2 minus 2, obviously that cancels out. And we have 4 times sine squared 2t. That's a product of 2 squares. So I can take out a factor of 2, take out a factor of sine, and this actually just simplifies to no radical, just 2 sine squared, 2 sine of 2t. So there's our sine u du, right, because we have that factor of 2. That's actually kind of nice for us. What's the integral of 2 sine of 2t? Mm-hmm. So I'll drag the negative outside. And then let's see, we have cosine 2t would be pi, cosine pi minus cosine 0. Cosine pi is -1 minus 1. So that's a -2 inside. Multiply that by -20 and we get positive 40. The integral, like we didn't need to use like any substitutions except for I guess 2t, right? If u is equal to 2t, we just sort of kind of did that mentally, but didn't need to use integration by parts or trigonometric substitution or partial fractions. Once we simplified, the integral ended up being simple. But there was, a hefty amount of algebra and trig identities to use to kind of get it to look so simple.
Do you use the double angle or the half angle if that's
I use the double angle.
double angle? Okay,
Mhm. Okay. All right, one more to go. Are you ready? If you liked arc length, you're going to love surface area. This is really similar, to the last one. The formula looks similar to the one we saw back in chapter 3 of our notes, and also like it's a similar like how we get this integral formula like from the last one we just learned is kind of similar to how we got the surface area from the arc length back in chapter 3. So it still involves that same radical, right? The square root of the sum of those squares of the t derivatives. And then each of these factors in front is just a radius. So when we say revolving about the x-axis, if we're revolving about the x-axis and y is equal to g of t, then that is a radius. That's a distance from the axis, right? Because that's a vertical distance. And if we're revolving about the y-axis, then f of t is the x-coordinate, and that is the distance from the axis, from the y-axis. And of course, just like in chapter 3, we see that we've got that factor of 2 pi out in front. So let's do one more. So we've got a circle, x squared plus y squared equals 9. That's just a regular circle, centered at the origin with radius 3. And we're just looking at a part of the circle from 3, 0 to 3 root 3 over 2. And that goes from t equals 0 to pi over 3. You can sort of tell, like, it's this is radius 3, but if it were a radius 1, that'd be like 1/2 root 3 over 2, and that corresponds to pi over 3. So here's t equals 0, and this is t equals pi over 3. And we're revolving about the x-axis, so it's just this curve here, right? Just this part. But we're revolving that about the x-axis. So it gives us this sort of figure that we're looking at here. Now, one thing you might note is that they gave us this rectangular equation, x squared plus y squared equals 9, but we can represent C parametrically. If we can represent this curve parametrically. This one's not too bad because it's just an arc of a circle. So the coordinates on the circle, the x-coordinate is always given by cosine, the radius times cosine, and the y-coordinate is always the radius times sine. So x is 3 times cosine t, and y is 3 times sine t. And we're looking at that on t ranging from 0 to pi over 3. So looking at that integral formula up there that we're going to use, we're revolving about the x-axis. So that is the top one here. Right, so we're going to use for revolving about the x-axis, we're using g of t or y, right, for our radius. And we need to find those derivatives. So let's go ahead and find those derivatives. What's dx dt? Negative 3 sine t. What's dy dt? 3 cosine t. Great. So S is 2 pi times the integral from 0 to pi over 3. Our radius is the g of t, is the y function. So this is 3 sine t times the radical of, I'm going to add these squares, so negative 3 sine t squared plus 3 cosine t squared dt. There's the integral that represents that area. Couple things we'll do. I'm going to yank this factor of 3 outside and also just square those out inside, like square out those products. So, so we have 6 pi times the integral 0 to pi over 3. And then inside the radical, we have 9 sine squared t plus 9 cosine squared t. We have a common factor of 9. Let's factor that out. we have this factor of 9 sitting inside a radical. I'm going to pull it out the radical, and in fact, pull it out the whole integral. And of course, when you do that, it'll become a factor of 3 outside. And then inside, what we're left with inside the radical is sine squared plus cosine squared. And that looks pretty familiar. That's just 1. Oh, and hold on one second. I'm going to point out I made an error that is fairly simple to chase down, but up here in this first line, I had this factor of sine t outside, which should be there, and then I seem to have just dropped it on the next line. So I'm going to fix that. That's better. So what are we left with in this integral?
Sine t, dt.
Yeah. Yep. And so outside the integral, we have 18 pi. Integral 0 to pi over 3 sine t dt. And the integral sign is just negative cosine. So I'm going to just put the negative outside, I think. So negative 18 pi, and then cosine t from 0 to pi over 3. And this isn't too bad. Cosine pi over 3 minus cosine of 0. Cosine pi over 3 is a half. Cosine of 0 is 1. So we've got negative 18 pi times negative a half, and that gives us 9 pi for the surface area. Always end on one that's not too hard. How's that?
Yeah, because your X and Y are single components there. You don't have to go through the whole.
Yeah, I mean, we still have to go. I mean, it's probably about the same amount of work as when we did this type of thing in Chapter 3. It's just that our curve in the plane is represented with these two parametric equations. Questions? Okay. Don't forget, assignment 7 due Friday, December 13th. And then you have an assigned problem for test 4 that you'll find on Canvas. That's due the last day of classes. Our final exam is scheduled for Friday the 20th at 3. And yeah, let me know if you have questions. I'll see you all on Monday. Hopefully I'll have your problem sets graded for Monday.